Okay, these are some solutions for the special problems we did, and this is the worksheet we gave you. And I put some Lagrange error-bound problems on here to try. So just a few notes. So basically, here's kind of the definition of our bound. And the actual error is the difference of the function at a value and the expansion or the approximation to some order n. And then we just have, this is from our Taylor's formula. And this gives us our error. For n, this would be the f to the n plus 1 factor, n plus 1 derivative, etc. And this is for some c between x and a. A is the center, and x is whatever value we're working with. That's the tricky part sometimes to get out of these books. And then if we can bound the derivative, which is what we try to do with some m, we can find some m that the derivative for the c in between this interval, between x and a, if we can bound this by some m, then we're going to be able to find the error bound. We also have to remember that we also have to bound this. Okay, so take a look at that. Hopefully that makes sense. And this is the notation we'll try to use throughout the problems. Try to find the m and bound that, okay? So the first one was the natural log of 1.05. This is number 1 off your worksheet. Now there's a couple ways to do this. I realized this later. I probably should have given you the particular Taylor series to use, or expansion to use, because we have different derivatives, and the expansions would look a little different depending on what we use. So you could have done this a natural log of x plus 1 about 0, and that would work the same way. But since this is real close to the natural log of 1, I just used natural log of x. About a equals 1, that was my center. So right around this, I'm going to expand that, and hopefully it'll be close. So the natural log of x, I took the natural log of x, its derivative, second, third, and fourth derivatives, which we've done before, and then I just evaluated all those at the center, which is 1. Okay, so this is what we've done before with Taylor series, so this should be pretty straightforward. I wrote down the general form, which I always do, just using the Taylor's formula again, and then I substituted in. And hopefully this follows your work. And this is my approximation. Okay, so we've done enough of these, so that shouldn't be an issue. Just kind of working it out. Your Taylor expansion of the natural log of x about the center of 1. A equals 1. Okay, so that was the first part. And then the second part, we wanted to find f of 1.05, so we approximated that by p of 1.05, which ended up being, if you just would put this in your calculator, and then you could use var y vars, and you could put 1.05 in here, or you could work it out mechanically. I got 0.04879. Okay, so that was the easy part. Now let's talk about the error bound. And this is what we have here. So the error is equal, so r sub 4, because this is a fourth order polynomial, r sub 4 of x is the absolute value of the fifth derivative, x minus 1 to the fifth power over 5 factorial. And c is in my interval between 1 and 1.05. This was the x. This is the particular value I'm looking at. I'm trying to approximate, and this is my center. So if I took the fifth derivative, if you go ahead and take your fifth derivative, you got 24 over x to the fifth. All right. And you can see that from the first page. Now that's decreasing on this interval from 1 to 0.5, because as x gets bigger, this gets smaller. So it's decreasing. So as x increases, this decreases. So the maximum value for the derivative on this interval will be at the left endpoint, or at 1. So we can bound f to the fifth derivative of x by 24 over 1 to the fifth, or just 24. So that was my m. That worked out nicely. And then we must also bound x minus 1 because we're going to use the absolute values because we're going to separate these out. So be careful there, because the absolute value just gives you the distance, kind of like a distance formula. So keep that in mind. So we want to maximize this on this interval, and if I put 1 in here, I'd have 1 minus 1 is 0, so the 1.05 is going to be it's going to maximize it there. So this is my error which is less than m, that's the bound on the derivative, and then x minus 1 to the 5th over 5 factorial, that was 24, and remember the maximum this will be at 1.05. It's going to go from 1 to 1.05. You can always check it at 1, it's going to be 1 minus 1, which is 0, but at 1.05 it'd be 1.05 minus 1, which is 0.05, and that's bigger than 0, of course, so that's going to be the maximum. So here was our error bound. Again, remember we must also bound this. So we just calculate that out. So 24 over 5 factorial, well 5 factorial is like 5 times 4 factorial, and that's 4 factorial, so I could cancel that out. So this just ends up being the 24, and this is just as 120, and if you divide that you get 5 either way. So you calculate this out. That was your error bound. Okay? So we didn't have any trouble with that. And then number 2 was the natural log of 0.09, so I just used the same expansion, natural log of x about a equals 1, because, sorry, not 0.09, 0.9, 9/10. 9/10 is still pretty close to 1. Just like 1.05 was close to 1, 9/10 is close to 1, it's just on the other side. But since we're using absolute values, that's going to work out. So all I did was the a part, the expansion, I just saw number 1. I just took this off of the first one. So I use the same expansion. So you can see number 1 for the work if you want, or you can do it like that also. So there's your expansion, because they were very similar. And then piece of 4 of 9, piece of 4.9, I put 0.9 into this. If I still had my calculator from number 1, it would be fine. I just var y vars it again. Put 0.9 in there. I got negative 0.1054. Okay, so that's the A and the B part. Those were easy. Now, the C part is the bound. And hope you can read this. I kind of switched it in here to save paper. We'll try to zoom in a little bit anyway. There we go. Okay. So if you can see the work here. So we're now on the interval 0.9 to 1, 9/10 to 1. Remember, x is the 0.9, and a is the center. So between 0.9 and 1, we got 1/10 there to work with. And again, this was my 5th derivative, which is the same as from number 1. And we're going to bound that by m. And again, this is decreasing, so I'm going to use the left endpoint. So this now it's going to be 24 over 0.9 to the 5th, because it's decreasing, so I'm going to use the left endpoint. And the top is going to be bounded by 0.9, not the right endpoint, because the top, if I put 1 in here, 1 minus 1 is 0. If I put 0.9 in there, I get 1/10. And that's going to be bigger, so you can see as I get closer and closer to 1, this distance gets closer. This distance gets smaller. So what I want to start over here is at 0.9 again. So again, we want to maximize that. And that's the absolute value, so don't worry about the negative sign. So this is my error is less than m, x minus 1 to the 5th power over 5 factorial. Similar to what we had in number 1. So there's my 24, and there's my 0.9 to the 5th. Okay, that was at my m. And then the maximum this is going to be 0.9 minus 1. That's the absolute value. Okay, to the 5th over 5 factorial. Okay, and I think again you can see add 1. You can just try it. You put the endpoints in, you get a good idea. If I put 1 in here, okay, 1 minus 1 is 0. If I put 0.9 in there, even though I get a negative, I'm not worried about the sign because it's the absolute value. I get 0.1, and the 0.1 is bigger than 0. Okay. So in this case, we want x to be the smallest it can be to make this distance or this difference the largest it can be. So there's my values, so I just put those in. So 0.9 minus 1 to the 5th over 5 factorial. There's the 24, there's the m that we figured out earlier. And then this can be 0.1, and it's negative 0.1, but it's the absolute value, so it's 0.1 to the 5th, 0.9 to the 5th, and times 5 factorial. Now, 24, again, over 5 factorial. This is like 4 factorial over 5 factorial is just 5. So I just simplified that. And there's another way you can simplify this too. This is, we could put these all over 1/10, 0.1 over 0.9, which is the same if I multiply the top and bottom by 10. I got 1 over 9, so that's 1 over 9 to the 5th times 1/5. This is an easier way to calculate it out than when you calculate it. That was your error. Okay? So that was 2. So if that makes sense, take a look at the calculations. It should be easy to follow.